to look at the net torque is equal to I alpha. We need to use Newton's second law for rotational motion. The net torque, let's go ahead and call counterclockwise motion positive, since that's the direction this is going to rotate, and we'll call clockwise motion negative. Net torque means we need to add up the torques produced by every single force. Again, the normal force and the force of gravity, they're both acting at the center of mass, so they have no lever arm. Remember, torque is R times F, perpendicular component. If R is 0, then there's no torque. So the normal force and the force of gravity produce no torque. For force of tension 1 and force of tension 2, R is the distance from the rotation axis out to where the force is applied. So it's basically the radius of the pulley itself. It's the 15 centimeters. So we have R times force of tension 1. That's a torque. R times the force. Force of tension 1 is already perpendicular to R, so we don't need to worry about sine or cosine of anything. Force of tension 2 will be R times force of tension 2. That will be the torque. Tension 1, which way is it making the pulley rotate?
Positive.
Clockwise, positive direction. Force of tension 2, if it was all by itself, would make the pulley rotate counterclockwise. So it's negative. So that has to equal the moment of inertia of our pulley times the angular acceleration. Now I've just introduced a fourth unknown. Force of tension 1 we don't know. A we don't know. Force of tension 2 we don't know. Alpha we don't know. So we need one more relationship. This linear acceleration of these masses. Do you agree that every piece of this string will have the same linear acceleration as the two masses? Okay. The string is touching the outside edge of the pulley. How do we relate angular acceleration to the tangential acceleration of the outside edge of the pulley? The tangential acceleration is equal to the radius times alpha. So alpha is equal to the acceleration over the radius. So I'm going to put that in. Most pulleys I've seen are uniform discs. So we'll go ahead and assume this pulley is a uniform disc. So I will be 1/2 times the mass of the pulley times R squared. So this R cancels with one of these. But now I still have an R in every term. So they will all cancel. So we have force of tension 1 minus force of tension 2 equal to 1/2 times the mass of the pulley times A. We have 3 unknowns and 3 equations. So the substitution can now begin. Over here, let's solve for force of tension 1. I bring that to the other side and this over. Force of tension 1 will equal M1G minus M1A. This one, force of tension 2, will be M2A plus M2G. So let's take those and substitute them into this third equation. So force of tension 1 minus force of tension 2. So minus M2A minus M2G equals 1/2 MA. So I've just taken force of tension 1, the M1G minus M1A, and put it in for force of tension 1. Then I took force of tension 2, the M2A plus M2G, and plugged it in for force of tension 2. And of negative because the equation had minus force of tension 2. And that all equals 1/2 MA. A is the same. Go ahead. Sorry.
Isn't it 1/2 MR squared?
The R's canceled.
But that's all of the R's. One R.
All of the R's canceled.
Show me, please.
There was an R right here. A over R canceled with one of them.
Right.
And then there was an R in every term, so that canceled the other one.
Okay. Thank you.
So the A's here are all the same. So let's get them on one side. We can factor the A out and then divide. So A is going to equal M1G minus M2G all over M1 plus M2 plus 1/2 the mass of the pulley. Since there's an M in every term, we can't cancel it, but we can leave our masses in grams because the units will cancel. So M1 we can leave as 200 grams. I'm going to factor out the G. So minus M2, which is 100 grams, times G, which is 9.8 meters per second squared, all over M1 plus M2 plus 1/2 the mass of the pulley. So all the grams cancel, that leaves us with units of meters per second squared. So the acceleration, actually of either mass, not just mass 1, the magnitude of the acceleration of either mass is 3.1 meters per second squared. Mass 1's heading down, mass 2's heading up, but they both have the magnitude of 3.1 meters per second squared. The acceleration of the outside rim of the pulley is also 3.1 meters per second squared. If we wanted to know the angular acceleration of the pulley, we could come back. Now that we know A, if we divide by R, we would know the angular acceleration. Okay, so we'd know the radians per second squared of the pulley. A little more involved when we have pulleys and masses, but still doable. We can use regular F equals ma for the objects that are still moving in a straight line, but we have to use the net torque is equal to I alpha for the object that's rotating, in this case the pulley. This acceleration will be constant as long as M1 doesn't fall enough where M2 hits the pulley, and as long as M1 doesn't fall far enough to hit a table. This acceleration will stay constant, which means you could use kinematic equations to figure out how fast they were going after a certain distance. You could also use energy, actually, too. If all we wanted to know is how fast they were going, we could use energy to look at that. If you don't care about the acceleration, you can use energy, which is nice.